So I specifically wanted to talk about capacitive pressure sensors today. And we'll go down a little bit of a tangent here in a few minutes, just because the math that I did doesn't agree with the textbook, so we'll talk our way through things. So in a capacitive pressure sensor, essentially we are just going to be directly measuring diaphragm displacement by referencing it to some sort of fixed electrode. So as a physical system, it's going to look something akin to this. And essentially, I'm just going to flip my diaphragm upside down from what we saw when I drew the original pictures when we were talking about piezoresistive pressure sensors. So here's my membrane. And then I'm going to draw a substrate down here below. Like so. And I'm going to have some sort of insulating material separating my substrate and my membrane that's going to leave behind essentially a gap that is going to be either at a vacuum pressure or some specific fixed reference pressure. Okay. So we literally can't do a full-on differential pressure measurement like we could with a piezoresistive because of the physical orientation of this system. Okay. So we are going to have a little bit of a problem, and it's a math problem here. So every time that we've talked about parallel plate capacitance measurements, we've been dealing with essentially the expression C is equal to epsilon A over D, right? Where our plates were in parallel. But when we have a pressure sensor like this, our plates are no longer going to be in parallel because the entire plate doesn't deflect, right? It's fixed at the edges. It's only going to deflect towards the center, and that deflection is a function of position. So instead, we're going to have to look at this integral. For a square pressure sensor, or for a square membrane of length 2a on each side, we're going to integrate from negative a to a. In the x direction, we're going to integrate from negative a to a in the y direction, and we are going to be integrating our permittivity over d naught, which is our nominal gap distance, minus our deflection as a function of position with respect to the x and y directions of our coordinate system, okay? Now, this equation does not have a closed form solution. It is not something that's particularly easy to do. However, so this is our general equation. If W as a function of x and y is much smaller than D naught, we can use a Taylor series expansion. And what we'll find is that that term 1 over D naught minus W as a function of x and y can be approximated as 1 over D naught multiplied by 1 plus W over D naught. And substituting this in, we are going to have an approximate capacitance of the integral from negative A to A, negative A to A, of epsilon over D naught times 1 plus W over D naught dx dy, or approximately C naught times 1 plus WA over D naught. So now I've introduced this other thing, WA, so let me explain what the hell that is, okay? So where WA is the, let me write it out here, average membrane deflection. And this is where I'm in a little bit of a pickle with the math, so to speak. So we're going to talk our way through this. So how we're going to take the average membrane deflection is literally we're going to integrate over the entire surface of the membrane and then divide that by the area of the membrane. So in the textbook, we get 1 over 4a squared multiplied by the integral from negative a to a, negative a to a of w as a function of x and y dx by dy. And Dr. Kajakari got 768 times our differential pressure P times a to the fourth power 1 minus Poisson's ratio squared, all divided by 10,575 times Young's modulus times the thickness of our membrane cubed. Okay. So for what it's worth, I guess, for lack of a better word, I didn't get that result. So let me go to a different page here. And now this is the tangent thing to where if you want to just check out for 5 minutes, feel free. And if you want to pay attention to the math and help me figure out where the hell things are going awry, that'll be great. Okay. Sure.
It's a, you wrote 786, but said 768.
It should be 768. Thank you for that, North. I transposed those two numbers. You are absolutely right. That is P as in the differential pressure. Poisson's ratio, that's correct. So P is differential pressure. A is half the length of one of the sides of the square membrane. Nu is Poisson's ratio. Capital E is Young's modulus of elasticity. H is the thickness of the membrane. All right, time for fun with math, or, whatever. So from my notes from the other day, I said, or actually this is, let's see, W as a function of X and Y for a square membrane was 12 times 1 minus nu squared PA over 4, or excuse me, PA to the fourth power over 47 EH cubed times 1 minus x squared over a squared quantity squared times 1 minus y squared over a squared quantity squared, right? So if we try to do that integration, and again, this isn't critically important, I just want to give you guys as accurate of a thing as I can. Our capacitance should be, so I have 1 over my area, which is just 2a quantity squared. Then I'm going to be integrating with respect to x and y, which means that this whole first term is a constant, so I can just pull that out and not have to worry about it. So 12, 1 minus nu squared, PA to the fourth power, 47 EH cubed. Now I'm integrating with respect to x, and I'm just going to split these integrals up essentially because they don't mess with each other. I can't think of a better word than that right now. So we would have the integral from negative a to a of 1 minus x squared over a squared squared dx, and then the integral from negative a to a of 1 minus y squared over a squared quantity squared dy. Okay. So let me just do something down here really quickly. So 1 minus x squared over a squared times 1 minus x squared over a squared is going to be 1 minus 2x squared over a squared plus x to the fourth over a to the fourth. So let me start by, did I FOIL that out correctly? Or did I make an 8th grade math mistake? I believe I FOILed it out correctly, right? So if we integrate this thing, that's going to look like, so let's see, I'm integrating with respect to x. So I'm going to have x minus 2x cubed over 3a squared plus x to the fifth over 4a to the fourth power. And this is going to be, oh, sorry, there should be a 5 right here. And this will be evaluated at minus a and positive a. So we're going to have a minus negative a is going to look like 2a. We're going to have, let's see, minus 2a cubed over 3a squared minus 2 times negative a cubed over, actually that one should be a plus 3a squared. And then we're going to have plus a to the fifth over 5a to the fourth minus negative a to the fifth over 5a to the fourth. Are we okay with that? Anybody see any error? Okay. So for what it's worth, I think I understand what Joaquin is saying. So this minus sign right here is why I'm getting this guy. And when I subtract, I flipped the second part. This plus sign right here gives me the plus sign here. And then when I subtract the lower limit, that's where I have that negative number there. That there is going to be some playing around with things here. So let's just see how this goes from this part. So I've got 2a, then I've got a minus 2a cubed over 3a squared. That's going to be, let's see, so Negative a cubed is just minus, right? So that's minus 2a cubed over 3a squared. Then I've got a to the fifth over 5a to the fourth. And now I'm going to have minus negative a to the fifth is going to look at plus a to the fifth over 5a to the fourth. And let's see here. So I'm going to have a least common denominator of 15. Then I have 2a minus 2a is negative. Actually, let me just get rid of some of these things real quick, right? So a squared is going to cancel that, so I'm just going to be left with a. This guy is going to cancel that. A to the fourth is going to be cancel that fifth. This a to the fourth is going to cancel that fifth. So 4/3 expressed in terms of 15. So 4 times 15 is 20. Let's see, so 2a over 5 is going to be the same thing as 6a over 15. Does that sound right? So 30 minus 20 is 10 plus 6, so 16a over 15. That's not what I got 4a over 3 earlier. Okay. So that's 30 over 15. Minus 20 over 15. Six over 15. 30 minus 20 is 10. Plus 6 is 15. Anybody see an error? So for what it's worth, if that whole thing right there is 16a over 15, this whole thing right here is also going to be 16a over 15 because it's literally the exact same integral, right? So let's see how that goes. I'm going to feel like a darn fool idiot if that was the mistake that I made earlier. Is just literally with the easy part of integration, and it's not just some weird thing. But anyway, so let's see what's going to shake out from this. So I'm going to have 1 over 4a squared times 12 times 1 minus nu squared pa to the fourth power 47 eh cubed 16a over 15. 16a over 15. Let's start canceling some stuff out. So this a times this a cancels this guy right here. 12 times 16 times 16, 3072 pa to the fourth 1 minus nu squared 4 times 47 times 15 times 15, 42,300 cubed. Let's see. Just as a heads up, 3072 over 42,300 is 0.0726. $768 over 10575. 0.0726. Well, son of a bitch, I made the error. It's not the textbook. Damn it, that's right. Okay, that's fine. Totally fine. So that is legit. Feel like an idiot. For what it's worth, I legitimately used an online integral calculator to make sure I was right, so I must have typed something in wrong. I feel like a buffoon, but that's okay. It won't be the first time, definitely won't, or isn't the first time, definitely won't be the last. While I was walking to class, because so just for what it's worth, part of this thing here arose from the fact that the textbook that I was looking at actually did not have anything for circular capacitive membranes. And so I was trying to follow along and make sure that I understood the process so that I could derive that. And then I was getting an answer that didn't make sense there. And then when I was walking to class, I realized it's because I forgot the differential area for a circle should be RdRd theta, not just drd theta. And so now all my math for that is definitely wrong. So let's fix that as while we're at it. Okay. So I feel like a goofball, but it is what it is. So suffering through more fun time with math. For a circular membrane, let me find those notes really quick. Here we go. We had W as a function of R was 3 times 1 minus nu quantity squared PA to the 4th power over 16 EH cubed. This was times 1 minus R squared over A squared squared. So for us to find our capacitance, that would be 1 over our area, which is just pi times the radius squared, actually, so that should be an A there, my bad. That 3 times 1 minus nu squared PA to the 4th power, 16 EH cubed, all comes out. And now I'm going to integrate. So I'm going to have an integral from 0 to 2 pi of d theta, which is literally just going to pull out a factor of 2 pi. And then over here, I'm going to have an integral from 0 to a of that 1 minus r squared over a squared squared times r dr. Or that r dr is my, or the rd theta is my arc length, and I just moved the r over to the part of the integration where it actually matters. So this guy just looks like 2 pi. Then we're going to have, let me scroll up here real quickly. Oh, of course I erased the damn thing I needed, son of a bitch. So I'm going to have r times 1 minus r squared over a squared times 1 minus r squared over a squared. So it's going to look like r times 1 minus 2r squared over a squared plus r to the 4th over a to the 4th is r minus 2r cubed over a squared plus r to the 5th over a to the 4th. Did I distribute my r correctly? Let's start there.
Is that not what we just solved with the from A to A? That's the problem.
No, because it's each term is raised to one more order of r. So it's very, very similar, but it's not quite the same thing, and so it's not going to have quite the same integral. That explains why. Okay, so when I did it without that, I got 8 over 15 earlier. So that thing being 16 over 15 actually makes way more sense because I was integrating over twice the length, so it would have been twice as big. Okay, so I should have noticed my mistake the first time. Sorry. So integrating this thing, we're going to have r squared over 2 minus, let's see, 2/4 is going to be r to the 4th power over 2a squared, and then plus r to the 6th over 6a to the 4th power. All of this is evaluated at a and 0 because we only have to integrate out from the origin out to the edge. So that's going to make this real easy, I think. So that's going to be a squared over 2 minus a to the 4th over 2a squared plus a to the 6th over 6a to the 4th power. So that's, well, let's just do it out this way. A squared over 2 minus a squared over 2 plus a squared over 6. Does that look right? Those guys cancel each other out. Just a squared over 6. I'll be damned. Get rid of all this crap. Calculus live. Okay, so I'm going to pull that factor. So let's see. So I'm going to have 2 pi over pi a squared, 3, 1 minus new quantity squared, pa to the 4th over 16 eh cubed times a squared over 6. The pi cancels the pi. The a squared cancels the a squared. 2 times 3 is 6 over that. Oh, wow, this comes up really dope. So that's just going to be 1 minus new squared pa to the 4th over 16 eh cubed. And the units actually work out right this time. That's great. So let me go back to page 1 just so I can finish this up. Using a similar derivation that we literally just did. For a circular membrane, WA came out to be PA to the 4th power 1 minus nu squared. I'm going to go back to that last page so I can find that. 16 EH cubed. Great. I'm sorry, what? So let's go back here. So I say that the 3 canceled out because 3 times 2 is 6, and I had a factor of a squared over 6, so the 6's canceled each other. So the W part, for what it's worth, or maybe that shouldn't have been C. This was WA. That's my fault for putting a C there. It should have been WA the entire time. Yeah, so there was originally a 3. It was right here. But I said that that 3 times that 2 from the 2 pi is 6. And then I canceled out the 6 down here. So that's where I got rid of the 3. The pi is canceled because I had 2 pi over pi. The a square is canceled because I had that. So the only thing that survived is this business right here. So, okay. So now we have an expression for the average deflection for a circular membrane that literally wasn't even in the textbook. So look at us doing math. Okay.
Does the relationship of C naught one plus WA over D naught still apply with this circular?
It should, because that was just generically for, that's just using this first order Taylor series approximation where it really doesn't depend on X and Y at all. It's just we have 1 over D minus X is 1 over D times 1 plus X over D approximation. Yeah, so it should be equally valid because the X and Y literally make no difference in that Taylor series approximation. Okay, so sorry for the fun with math interlude there. I legitimately tried to do that in my office for 45 minutes, and I feel really embarrassed that I walk in the damn room and actually got it right. But hey, at least it's right now. So that's all I wanted to talk about capacitive pressure sensors. We can now see, obviously, how the capacitance is going to change approximately for varying pressures and all of that kind of good stuff. And then we could relate it to our electrostatic sensing notes and all of that kind of stuff to talk about how we could convert that change in capacitance into an electrical signal. Okay, so now back to more relevant topics. Let me put all these pages of gobbledygook in the right order real quick. Thank you for bearing with me. Let's talk about piezoelectric actuation. Okay. So when we were talking about sensing, I think the first thing that we talked about was piezoresistive sensing, right? Or maybe we talked about capacitive sensing first, and then piezoresistive sensing. We've talked about capacitive actuation. This is maybe a silly question, but why aren't we talking about piezoresistive actuation? It doesn't exist. If we pass a current through a resistor, does it change size or does it deform? If we heat it up enough to release its magic smoke, maybe, but under normal operation, it does not. So there is no piezoresistive actuation to worry about. So that's why we're moving on to another topic, right? So piezoelectric actuation. All right, so piezoelectric actuation, put most simply, just uses the inverse piezoelectric effect to generate mechanical deformation in the presence of an applied electrical field. So when we were talking about piezoelectric sensing, we had a relationship that T, which was our stress in pascals, was equal to E times S. So that's our Young's modulus measured in pascals times our strain, which is a unitless quantity, minus lowercase e, our piezoelectric coefficient, times uppercase script e, where this was our electric field in volts per meter, and our piezoelectric coefficient had units of coulombs per meter squared. Okay, so exact same relationship as we saw before, we're just using it in the opposite direction. So earlier we saw essentially that if we mechanically deformed a piezoelectric material, it generated some electrical signal, which I think we called it a motional current because it was related to the rate of change at which we are mechanically deforming the piezoelectric material. Well, we're going to see now that we're going to generate forces that are related to the rate of change of how quickly we are applying a voltage across our device or our piezoelectric actuator. Okay. So in general, the displacement induced by a piezoelectric actuation is very small. However, I did not spell that all the way. This actuation scheme has several advantages. And let's talk about those really quickly. So the first of which is in direct comparison to capacitive actuation. Okay. So in capacitive actuation, doesn't matter if we were using a DC signal to generate our force or an AC signal to generate our force, there was still going to be DC power consumed because the force was proportional to the voltage squared. And we know that the square of an AC voltage still has some DC term. We saw that 1/2 VAC squared term pop up over and over and over again whenever we had any kind of AC signal. So there was always DC power being consumed. So piezoelectric actuation does not consume DC power. So that is good. Second advantage is that the instantaneous force is generated in response to an applied electric field, meaning that there is no delay or anything like that between when we apply the voltage and when we experience the force. As soon as we apply the voltage, the force occurs. And then as soon as we take the voltage off, the force stops happening, and so on and so forth. And then lastly, and this is a key thing here, we'll see that the magnitude of the generated force can be rather large. So because of these advantages, piezoelectric actuation is used in a lot of commercial devices that we see in our everyday lives. Piezoelectric actuation is used in inkjet printheads. So effectively, we deform a piezoelectric actuator to squeeze ink droplets out through a nozzle. Piezoelectric actuation is part of all of our digital watches, cell phones, and all of that kind of stuff. It's usually a piezoelectric resonant crystal that's providing the timing for everything. So if we excite it at a fixed frequency, it oscillates at a fixed frequency. Joaquin? Sure.
Saying, for instance,
Right. So if we if we apply an AC voltage across it, it will generate an AC force without any DC component added to it. Right. Yeah. Another place where you might see piezoelectric actuation is used in the generation of what are called surface acoustic waves. And you can use those surface acoustic waves to actually induce an electric signal in a second piezoelectric crystal. That's used particularly in some biomedical sensing applications. So let's talk a little bit about the actuators themselves now. So we're going to have both longitudinal and transverse piezoelectric actuators. So picture I have here, I'm trying to remember what colors I used from a couple of weeks ago when we talked about piezoelectric sensing. So I'll try to do the same thing. So here is our crystal. I'm going to put a electrode on top and bottom, like so. This dimension is going to be our height. This is our cross-sectional area. I'm going to call this A1. This is our area A3. And if we are able to generate an electric field in this direction, so this will be the 3 direction, what we should see is a force generated in the 3 direction as well. And for what it's worth, the coordinate system I'm using, 3 direction is up and down, 1 direction is horizontal. So this is our transverse actuator, I believe. Let me double check. This is actually the longitudinal, sorry. The reason why I was slightly confused is because in a longitudinal actuator, we would expect it to be effectively extending along the length direction. But if we're thinking about what we're doing here, so this is kind of an odd-ish thing, okay? Essentially, all of the math that we're about to do is effectively proving that this piezoelectric crystal is acting like a spring in extension. That's literally all that's happening. If we apply a field in this particular direction, the material is going to stretch in the same direction like so. So over here, I'm going to do our second actuator. So once again, drawing our little picture here. So if I've got an E field in this direction, here's E3, I should be able to generate some transverse force as well. So that I'm going to call F1 coming out of the sides like this, where my critical dimension in this case, instead of being the height, is actually the length of the actuator. Here's my cross-sectional area A1 yet again. This is my cross-sectional area A3 yet again. Okay, so shitty pictures aside, essentially what we can see is that it's possible to generate forces in both the longitudinal direction and the transverse direction with one of these actuators, and it's going to be dependent on effectively which of the piezoelectric coefficients is stronger, whether it's going to be the E33 or the E31 coefficient. So let's start by looking at longitudinal actuation. So for longitudinal actuation, we are going to have the relationship that T3 will be equal to ES3 minus E33, and then electric field 3. And I'm going to make a note here that lateral stresses are ignored. So if the piezo material is free to deform, then our stress term T3 must be 0, which yields the relationship ES3 must be equal to lowercase e33 script E3. So effectively, Young's modulus times our strain will be equal to the piezoelectric coefficient multiplied by the applied electric field. Okay. So this E3 term is nothing more than the voltage that we've applied across our transducer divided by the height of our transducer. Electric field is simply voltage over distance, right? So we could rearrange this and we could find that our strain S3 is nothing more than E33 times our electric field over Young's modulus. And this becomes E33 times our voltage over Young's modulus times the height of our crystal. Okay. So for a uniform strain, S3 will just be the change in height over the nominal height, giving us a change in height of E33 over Young's modulus times our applied voltage. So this is fairly interesting because our displacement in this longitudinal actuator does not depend on the geometry of the system literally at all, only on the material through Young's modulus and the piezoelectric coefficient and the amount of applied voltage. So essentially, if we had a piezoelectric crystal and I applied some specific voltage across it, it will increase in height by some fixed value delta H, okay? If I take that voltage away, it goes back down. And if I apply it again, over and over and over again cyclically, I generate essentially an AC force.
Can you make material shrink by doing the negative voltage?
Yes. Actually, I say yes arbitrarily. I believe the answer to that is yes. I seem to remember me and my lab mate doing something like that in graduate school, but that has also been at this point 12 years, so I could be misremembering things. So I will happily look into that. Let me put a note on it, but I believe the answer is yes. So can you shrink a piezo material? All right, I will note to look into that. Thank you for the question, North. So let's work a quick example here. So let's say that we have PZT4, piezoelectric coefficient of 15.1 coulombs per meter squared, is a ceramic piezo material used in many commercial devices. And it can also be used to make thin films. So, if its Young's modulus is E is equal to 110 gigapascals, what voltage is needed to induce a displacement of delta H is equal to 50 nanometers. So this is simple solving for V, essentially, if we know what delta H is, right? So moving things around, our voltage would be equal to delta H times Young's modulus over E33. So we would have V is equal to E delta H over E33. So it's going to be 110 gigapascals times 50 times 10 to the minus 9 meters over 15.1 coulombs per meter squared. And I got 364.238 volts. So I think, as I said earlier at the top of this material, the displacements that are generated are typically pretty darn small, right? So for a 50 nanometer displacement for this particular material, regardless of what its size of the actuator is going to require about 365 volts. Now, that amount of displacement is incredibly tiny. So one of the ways that we can generate significantly larger displacements with piezoelectric actuators is to essentially stack them up. Okay. So this is something that we actually did in my research group in graduate school. So I'm going to put a line under this thing. We're going to talk about this really quickly. So let's say that I have a source voltage, positive polarity on the left, negative polarity on the right. And essentially, I'm going to stack up a whole bunch of actuators here, right? So it might look something akin to this. This would work. And then here's my piezo material effectively inside each of these guys like so. So this would be 3 stacked up on top of each other, right? So I actually have to be careful about how I wire this guy. And I think this actually goes back to North's question. So essentially, if I wire, actually, sorry, the positive polarity terminal of my voltage to this top electrode, and I wire the negative polarity terminal to the bottom electrode here for my EE students, what's going to be the direction of my electric field?
Down.
Down. So this is going to generate some positive delta H based on how we've described all of our directions previously. Okay. Now let's say that I wire up these guys also. So what is going to be the direction of my electric field in that bottommost material? Well, it's also going to be down, right? I have positive polarity electrode on top, negative polarity electrode on bottom. But this one in the middle is going to have a field in the opposite direction because its negative polarity electrode is on top and its positive polarity electrode is on bottom. And so what we're going to wind up seeing is that our net delta H is simply the number of individual actuators that we have stacked together multiplied by E33 E over V, like so. So we can stack a whole bunch of actuators together. And again, each individual actuator can be incredibly thin because the geometry of the actuator doesn't matter, and we can generate relatively large displacements because if we generate a small displacement for each one, but we put 50 of them together, we get 50 times the displacement out of our system.
So I have a question based off of this. In this case, we have 4 actuators and 3 electric fields, right?
We have 3 actuators, but we have 4 electrodes.
Okay.
Jordan, what was your question? Yeah. So the direction of the electric field depends on whether the positive polarity side is on top or bottom. So electric field is always oriented from positive polarity to negative polarity. So because the positive polarity terminal is here and here, and our negative polarity terminal is here to here, we see that for this guy right here, so it's positive to negative, so that's why we have these guys down. This guy is positive to negative, so that's why we have these guys down. But for this guy in the middle, it's positive on bottom, negative on top, which is why the field is oriented up. Correct. So essentially, we have a capacitor that happens to grow or shrink depending on the voltage that we apply to it. So even though we're applying a DC voltage, there is no current flowing between the electrodes, which means there is no power being consumed. And sorry, just to reiterate one thing really quickly, We are not going to, so if we apply a DC voltage like this, we're going to see an instantaneous change in we're going to see that deformation. That deformation is effectively going to be held at this specific height until we remove that voltage from the system. So we can instantly cause our stacked actuator to increase in size by some fixed amount. It is consuming no DC power. As soon as we release or remove that DC voltage, it shrinks back down, but there's still no actual power consumption during that process. Hannah? Yeah. So that goes back to the question that I need to answer for North. I believe that all three are expanding, but if that is the case, then it turns out that you can't make them shrink. So that's what I want to double check. So Jordan's posited that we could potentially make actually, so what Jordan had posited was that we could make the middle layer thinner. So if the direction of the field, and I apologize for not knowing the answer to this question off the top of my head, but if we could make the middle layer thinner, then the field for that middle layer, we could potentially induce a different displacement in that one that could be counteracted. But I don't think that that's actually true because our displacement isn't dependent on the field. It's dependent specifically on the voltage. So the short answer is, let me get back to you guys for the next class meeting to make sure whether or not we can cause them to contract if we apply a negative voltage. But the more I'm thinking about it, the more I believe the answer to that question is no. I don't think the polarity of the voltage particularly matters. But I've been wrong about other things like simple math even earlier today. So I will get back to you on that one. I'd rather say I don't know than tell you incorrectly. All right, so one last little thing for today. So I want to talk about force, okay? So it is often useful to model the piezoelectric effect as a force acting on the boundaries of the transducer. And this goes back to what I was talking about essentially treating each of these individual transducers as just a spring in extension, okay? So our piezo, so if we think about this in this way, so let me write force here, okay? So generally speaking, for a spring in extension, we have F is equal to Kx, where X is our displacement, okay? So what we are doing is we're replacing X with our change in height because that is the amount of displacement our spring is seeing. So our spring constant in this case is going to be EA over H. Well, if we look at this, we have a delta H over H. That is literally just our strain. So we would have E times A times S, and S coming from back up here is simply E33, our piezoelectric coefficient, times our field over our Young's modulus. So that's going to be EA piezoelectric coefficient field divided by Young's modulus. These guys cancel each other out, and we find that the force of our piezo element that's generated is, in this case, going to be E33, A3, E3, or putting it in terms of the applied voltage, which might be useful, would be E33, A3 times our voltage divided by our height. Where, for what it's worth, if you go back to our notes, this EA over H relationship is literally just the spring constant for a beam and extension. Okay. So for the PZT4 actuator, from the previous problem, what force would be generated if the actuator area is A3 is equal to 16 millimeters squared. So that's 4 millimeters by 4 millimeters. So we're stretching the order of micro scale here, but that's okay. And the actuator height is H is equal to 1 millimeter. Okay. So plugging in our values here, we would have our E33 was 15.1 coulombs per meter squared. Our area was 16 millimeters squared. Our voltage was, let's call it 364 volts or something like that. And our height of 1 millimeter, we wind up actually generating a force of approximately, goodness gracious, my handwriting is getting ridiculous, 88 newtons. Now, that is a relatively large voltage, 364 volts, and that is a relatively large piezo actuator because it's 4 millimeters squared and a millimeter thick. But I mean, that's definitely smaller than our fingertips or anything like that. And we're getting 88 newtons of force generated out of that. Now, when we were dealing with electrostatic actuation, the few example problems that we worked, and granted, we were dealing with plate areas on the order of 100 microns squared or 1,000 microns squared. But what kind of forces were we getting? Micronewtons of forces. So we are only 1 order of magnitude up in size, but we're about 3 orders of magnitude up in force as compared to our electrostatic actuation forces that we were generating. So piezo actuators can actually generate a very considerable force for such a small package. All right, that's enough out of me for today because it's 1:45, which is when the class is supposed to be over. I will go look up the answer to this question before I forget about it, North. Thank you very much for it.